We've covered weather theory. Now we're going to talk about what that theory actually causes to happen when weather forms. We'll talk about several weather patterns in this segment. First, we'll talk about cyclones and anti-cyclones. This is the wind flowing around low pressure and high pressure areas. Next, we'll talk about frontogenesis and frontolysis, the creation and destruction of fronts which move across the surface. Last, we'll talk about specific types of fronts, cold fronts, warm fronts, and occlusions. We'll also spend a little time on stationary fronts. First, we'll talk about cyclones. Cyclones are characterized by low pressure. This low pressure causes convergence. As air flows into the low, it converges. As it converges, the air in the low already is pushed upward. We've learned earlier that when air is pushed upward, it tends to cool and that it in turn causes condensation. So we have an increase in clouds, typically in cyclones, and finally, we have a counterclockwise wind flow. You'll remember from the meteorological theory that the air will tend to flow along the pressure gradient force directly into the low. But the Coriolis force will tend to push it to the right. So we'll get air flowing counterclockwise around the low pressure area. Anticyclones, on the other hand, are characterized by high pressure. This high pressure tends to cause air to move out of an area, and so we have subsidence. That is, air moving down and away from the center of the high. We'll generally have clearing conditions in anticyclones, or high-pressure areas, caused by the fact that the air is moving down, and therefore warming and able to hold more moisture, and because it is moving away from the center of the high. And finally, we'll have a clockwise wind flowing around anticyclones. Again, the pressure gradient force directs the air out of the high, and the Coriolis force pushes it to the right. That causes a clockwise flow around the area of high pressure. For the rest of this segment, we'll talk about weather fronts. We'll begin by talking about how fronts form. This is called frontogenesis. Fronts form when two air masses, remember, two very large bodies of air, are pushed together, typically by wind. The two air masses must have a sharp transition in density between the two, and that can be caused either by temperature or by humidity, both of which will change the density characteristics of the air mass. As more contrast develops, that is, as the air masses are pushed closer and closer together, we'll get a wind flow, and this will typically cause a stationary front development, as you can see in the figures. We've just seen how fronts are formed. But fronts also dissipate or are destroyed in a process called frontolysis. This happens because the adjacent air masses modify and equalize eventually across the front. Remember, air masses have a specific temperature and humidity characteristic, but after a while they take on the characteristic of the region they are in. This will eventually cause the front to dissipate. As the name implies, the stationary front does not move across the surface. Airflow is shown in the figures on this slide. If we look at the upper figure, we see cold air and warm air as viewed from the side. In the lower figure, we see the same thing viewed from above. We can see the wind flowing in opposite directions on opposite sides of the front. The front is typically designated by sharp barbs on the side opposite the cold air and smooth barbs on the side opposite the warm air. The fact that there are both sharp and smooth barbs indicates this is a stationary front since they are on opposite sides of the line. Stationary fronts will frequently generate frontal waves. We can see in Figure A a stationary front with cold air flowing in one direction and warm air flowing in the other direction on opposite sides of the front. Because of upper wind flow, I can sometimes get a bump in that stationary front, which will cause the air to begin flowing in slightly different ways. You can see in Figure B that the warm air has started to move northward and the cold air has started to move southward. This is accentuated further in Figure C, and now we can see that the air on the right side of the figure is warmer than the air it is moving into, and therefore we have a warm front symbol on that line. The colder air on the left side of figure C is moving into the warm air, and therefore it is a cold front. Cold and warm here are relative terms, not absolute terms. So the cold air is colder than the warm air, but that does not mean it's Arctic or frigid or anything like that. It just means it's colder than the air it's moving into. We can see in figure D, we've now begun to get a low pressure area at the top of the fronts, and the warm air continues to move. The cold air continues to move behind it, so now I've got cool air on the far right, a low pressure area, cold air, and warm air in figure D. Now in figure E, I start to see a cold front catching the warm front. What happens in that case is something called an occlusion. That is, I've got cold air underrunning the warm air, and we'll see a little bit more about that in a later slide. Figure F shows the full development of the occlusion. And finally, figure G shows the frontolysis, that is, the destruction of that front, and going back to a stationary front. So now let's look at fronts in a little more detail. We'll start with a cold front. In this figure, the upper part of the figure shows some cities in the central United States. The lower left figure shows the same cities, but as viewed from above as we'd see them on a weather map. You can see the isobars, the frontal boundary. The frontal boundary is the boundary on the surface, and you can see the station data for each station. On the lower right, you can see the METARs, or station reports, for each of these stations. To give you an indication of what each station is experiencing, let's talk for a minute about what happens when a front moves through. What's actually happening is that cold air is moving from the left to the right in the figure. As it moves from the left to the right, it's colder and more dense, so it pushes its way under the warm air. As that happens, air is forced upwards. We know when air is forced upward, it cools, and if there is enough moisture, condensation will occur and eventually precipitation will occur. So, what we see in the picture on top is cumulonimbus clouds ahead of the cold air, and then ahead of that are some other clouds. Behind the cold front, we see very clear air because the front has moved through and cleared out the area. The symbols on the bottom left of the screen show us that St. Louis now has partly cloudy skies and wind from the northwest. Indianapolis, on the other hand, which is just ahead of the front, has wind from the southwest and cloudy skies. If we move out to Columbus, the skies are mostly cloudy, and in Pittsburgh they are only partly cloudy. You can see in each of these areas that the wind is mainly from the southwest. There are two kinds of cold front actions. The first is the cold air front moving across and underrunning the warm, moist, stable air. In this case, the air will be pushed upward. The cold air is more dense and pushes the warm air up. Since the air is moist, we will get condensation and eventually precipitation. But since the air is also stable, we won't get air rising vertically. On the other hand, if I have a cold front underrunning warm, moist, but unstable air, I'll have the same characteristic of cold air pushing warm air up. That is, the moisture will cause condensation to occur and clouds to form, but since the air is unstable, the clouds will continue to rise and develop further and further. So I am much more likely in this situation to get cumulonimbus clouds. In addition, cold fronts have different speeds. Remember from earlier that the speed of the wind depends upon how close together the isobars are. The closer together the isobars, the faster the wind speed, and therefore, the faster a front will move. If we have a slow-moving cold front, we basically have a lower wind speed and isobars that are spaced further apart. A slow-moving cold front is characterized typically by colder air pushing under the warmer air, but it takes a little longer for the slow-moving cold front to pass and the weather is typically not quite as severe. In the case of a fast-moving cold front, the cold front pushes up the warm air, whether it is moist or not, very abruptly. That can cause cooling very quickly, which can cause a lot of energy to be released, which can cause very severe thunderstorms. On this slide, we've got an animation of a cold front. What we'll see here is a cold front, a fast-moving cold front with severe weather at the frontal boundary. As the warm air is pushed up over the cold front, it cools and condenses and therefore releases energy. On this slide, we see an example of a warm front where the warm air has ridden up over the cold, denser air as it moves from west to east. With a cold front, we saw most of the weather situated very near to the frontal boundary. Here we see the weather extending significantly to the east of the frontal boundary with clouds as far as 600 miles to the east. The clouds are also descending as we move to the west closer to the frontal boundary with rain clouds for about the first 200 miles. We can see from the weather chart on the lower left that we have winds from the southwest at St. Louis and from the southeast at the other three locations. We also can see that the cloud cover varies across these three sites, but most importantly, we can notice that the warm front air has a much larger area of impact than the cold front air. On this slide, we see two types of warm fronts. The first is characterized by moist, stable air. As this air is pushed up over the colder air, we get condensation and clouds. Since the air is stable, we get no vertical development, so while we'll get rain, it will be rain typically from stratus clouds. Next, we see a warm front consisting of moist, unstable air. In this case, the air is pushed up over the cold air, but since it is unstable, it continues to rise. In this case, we get extensive vertical development, and we may in fact even get thunderstorms in an area like this. What we'll see here is a warm front animation. We see warm air overlying or overriding the colder air below as the front moves forward. The frontal boundary on the surface, shown by the symbol, is well behind the warmer air at altitude, and therefore we see clouds forming well in advance of the front. One type of warm front that can give us particularly bad weather is a winter warm front. Winter warm fronts are typically slow-moving, and they are characterized by low ceilings and visibility and fog, rain, or snow. That means we're going to get low IFR conditions, instrument meteorological conditions. We have multiple freezing levels in this area. We have a freezing level above the warm air and a freezing level below the warm air in the colder air. You should also remember that a warm front does not necessarily mean that the temperature in the air behind the front is above freezing. It simply means that it is warmer than the air it is moving toward. Now that we've seen warm fronts and cold fronts, let's talk for a moment about frontal movement. Fronts move perpendicular to themselves. What that means is that if the front on a chart runs from north to south, its movement will be from west to east, so it moves perpendicular to its direction. A cold front moves at the geostrophic speed. Remember, that is the speed of the wind at 3,000 feet, and it basically parallels the isobars. A warm front moves at 2/3 the geostrophic speed, so eventually the cold front will catch the warm front. So, we've seen three fronts so far: the stationary front, cold front, and the warm front. Now we are going to talk about something called an occlusion. An occlusion is when a cold front overtakes a warm front. You can see in the figure, we have cold air moving towards warm air, which is being forced up, and the cold air is encountering other cold air. So, the warm front is basically being forced up over the cold air in front. We can see in the figure below, on the bottom, that we have a different symbol for an occlusion. We have the combined symbols for cold fronts and warm fronts being used. You can also see in the METARs that we have weather characteristics of a warm front ahead of the occlusion, and weather characteristics of a cold front behind the occlusion. There are a few characteristics that define an occlusion. One is a warm front occlusion, and the other is a cold front occlusion. A warm front occlusion occurs when we have cool air overtaking warm air, and the air ahead of the warm front is cooler than the air overtaking it. We have a cold front occlusion when we have cold air overtaking the warm air, and the air behind the cold front is colder than the air ahead of the warm front. What we see here is a top view. That is an overview and a side view animation of an occluded front. This is a cold front occlusion. You can see the colder air coming from the left, and it's running under the warmer air, which is in turn overrunning the cooler air to the far right. On the top view, that is looking down from above, we see the symbols gradually move from a warm front and a cold front to an occluded front. And in the side view of this animation, we see the weather ahead of the fronts look like warm front weather, and weather behind the fronts look like cold front weather. On this figure, we see a warm front occlusion. Cooler air is pushing up the warm front over the colder air in front. You can see the weather associated with that on this slide as well. And here we see a cold front occlusion. We have colder air behind moving under the warmer air, which is, in turn, moving over the cooler air in front. This is the end of this lesson.